This year, thanks, Adam. This year, we'd again like to thank the Physical Sciences area for providing funds for refreshments, as well as the Physics Division's Adam Foote at the back there for providing administrative support. Before I introduce you to today's speaker, I'd like to say thank you to our outgoing 2024 committee for a fantastic year of talks and instrumentation at all scales. We had the challenges of launching the Psyche mission to the asteroid belt from Livermore's Morgan Burke, all the way to using DNA to assemble nanoscales devices with UC Berkeley's Greg Tikhomarov. We also heard about the Engineering Fusion Mega Project, ITER, the complex from Berkeley Lab's own Bob Guinean, and cutting-edge quench detection from CERN's Emanuele Ravioli, and many more besides. So as always, if you want to look up at any of the previous talks, we have a YouTube playlist, which is linked on our website. We're a bit behind on catching up with some of the later talks from 2024, but those should be updated by February. So before we move on to our speaker, I just want to introduce our 2025 committee. Here they are. So this year we have early career and senior staff scientists from both the Physics Division and from the Molecular Biophysics and Integrated Bioimaging Division, the latter of which we haven't had on this committee for 10 years. So we'll be interested to see what contributions they can bring for this year's talks. Okay, so with that, I'm going to introduce our speaker. So today we are delighted to welcome Dr. Michel Piat, who is here at Berkeley Lab through the middle of 2025 on sabbatical from Paris Diderot University, where he holds the position of professor. Michel is an astrophysicist specializing in cosmology and instrumentation. He has worked on major CMB projects, including Planck HFI, QUBIC, and is now involved in CMB S4. He has expertise in cryogenic detectors, millimeter wave optics, and precision measurements. Michel has also contributed to several satellite proposals like PRISM and CORE. As a professor and researcher, he develops instruments to study the universe's early structure while mentoring young scientists. So let's welcome Michel.
Thank you. Can you hear me? It's okay? Okay. Thank you very much. Let me move this panel from here. Thank you, Rebecca, for the introduction. So it's a pleasure to be here to present you this instrument called QUBIC, QNU Bolometric Interferometer for Cosmology, which is an instrument we have been developing in Paris, especially with international collaborators, especially in Italy, for several years now. And that has been now installed on the observation site, as you can see in the background photo here. And in this talk, I would like to show you a little bit how we build this instrument, to give you some kind of an insight of how we build the instrument from the scientific objectives. So this is the outline of my talk. First, I will give you a brief cosmological context, so the origin of the cosmological microwave background and the polarization. Why is it important? Why is it interesting to observe this light? And after, in the second part, I will show you how we build QUBIC, so starting from classical radio interferometry to the instrument that we have built. I will show you in the third part the description of the instrument. And if I have some time, I would like to show you some very specific feature of QUBIC, which is spectral imaging, at the last part. So I start with this scientific context, cosmological context. So this is a picture I like very much. I took that from Jacques Delabrouille presentation. So this is a view of the sky in the far infrared wavelength, so roughly between 30 gigahertz to 1 terahertz in frequency. And as you can see, this is a very rich sky. You can see lots of things in here. First, of course, you see the Milky Way. This has been measured by the Planck satellite, by the way. What you can see, the bright part here is galactic Bremsstrahlung that you can see. And the huge emission from the galaxy are mainly due to dust emission. And what you can see here on the bottom and the top, so in the galactic pole, are tiny fluctuations of the cosmic microwave background And this is what we are interested in. But you can see that also there are lots of other science to be done with this kind of data. And if you add the polarization as well, you get also much more information, especially on the magnetic field of our galaxies. And this is very interesting also for astrophysics. So the origin of the cosmic microwave background. So usually it is explained with a chart like this, where here you have your favorite instrument, it is now, and you are looking back to the future. And since we know that the universe is expanding, we know that the universe was denser in the past. And so you arrived at a kind of singularities, which is called the Big Bang. And so since the universe was very dense at the beginning, it was in the form of a plasma, so the photons cannot escape from this plasma. And so we have to wait for 380,000 years to reach what is called the recombination. And from these moments, photons could escape from the universe and could travel all along in your universe to your favorite instrument. And this is what is called the cosmic microwave background. It's also called the 3K black body, 3K background, because its spectra is at about 3K, 2.7 something. And this cosmic microwave background has also tiny fluctuations, which mainly traces density fluctuation that were there when the CMB has been emitted. And so mapping this tiny fluctuation gives very interesting information about the universe. And if we add polarization on top of that, you have much more information, complementary information. So in here, so usually the CMB is linearly polarized, a few percent linearly polarized. This comes from the emission of photons at the very last scattering surface. And here you can see two simulations of polarization that has been made. And usually what we do is to decouple the linear polarization on the sky into two modes, what are called E modes and B modes. So B modes are curl components, while E mode are zero curl components. And what you can see in this simulation here is that mainly when you have density fluctuation that has produced CMB anisotropies, this mainly produce what is called E modes, and of course temperature anisotropy is what you see mainly in this graph. While you can have another source of CMB polarization coming from primordial gravitational waves, and this comes from the fact that at the beginning of the universe, the cosmological model predicts that there has been a very fast period of expansion of the universe called the inflation. And this very fast expansion period would have created gravitational waves that are still present, that will be very difficult to measure directly, but that has left specific feature in the CMB polarization, especially. These are B modes, because these primordial gravitational waves produce temperature, E modes, and B modes. And so this is the only way to produce primordial polarization, B modes, with these gravitational waves. So the level of this signal is very small, unfortunately. So if you look at the temperature anisotropy, roughly the RMS temperature in the sky is 100 microK. So that means that the CMB has plus or minus 100 microK fluctuation on the sky. Looking at the E modes, you have 1 microK. And if you look at B modes, which are not yet detected, you expect a signal that is less than 100 nanoK. So this primordial B mode signal has never been detected yet. It's what is called the smoking gun of inflation. And this is very interesting to measure because it's probed the inflation, so a physics that is not reachable from the ground. So the level of these B modes here is primordial B modes are given by a parameter, a cosmological parameter, which is called R, which is the scalar to tensor ratio. And the current constraint is to have this parameter less than 3%. So usually we like to present this kind of measurement in a power spectra. So this is the power spectra of the anisotropy on the sky. So you have here the power spectra for the temperature that has been measured very precisely by, especially by Planck. You have the E modes that are now very well known, that has been measured also as well. And you have potentially the B modes that you can see here in red. And this is as a function of the angular size on the sky. I've put here the multiple L and the corresponding angular size on the sky. What you see is that, and I will come back to that later, so the pyramidal B modes is relatively large on the sky. We are speaking of a few degrees patches on the sky, let's say 2 degrees on the sky. And so the signal is very small. We expect a signal much lower than 100 nano-K. So we need very sensitive experiments. We need a very low instrumental systematics. And the problem also are galactic foregrounds, because if you add the emission of our own galaxies on top of that, so cold dust and also synchrotron emission, you have this kind of bands for the emission of our galaxy, of the foreground, and you see that this band is dominant over the B modes. So to solve this issue, the only way is to measure the sky at different frequencies and model this emission and subtract that from your measurements. So before moving on with description of QUBIC, I just wanted to give you a fun fact. Do you know that if you want, you can detect the CMB from your garden? That's something that you can do if you want to try it. You can just use a satellite TV antenna. So a satellite TV antenna is, in fact, a quite sensitive radio telescope working at 10 gigahertz with 1 gigahertz frequency band with roughly, depending on the dish, about 5 degrees angular resolution. And I built that, I tried that. And this is the kind of measurements we were doing in Paris regularly with students. And inside Paris, we are detecting the CMB with this kind of instrument. Of course, you need some tricks to do that. You have to have some modulation to remove the 1 RF noise. You need to shield your instrument correctly because of side lobes. And maybe the most difficult part for if you want to do that in your garden is calibration with liquid nitrogen. That may be more difficult to have in his garden, and when you do that, you can measure what we call sky dips. So these are real measurements we did in Paris. So it's the emission, the temperature of the sky as a function of elevation. So we go from the zenith to the horizon and again back to the zenith, and we do that several times. And if you do that, you can plot the sky temperature as a function of air mass, which is roughly the thickness of the atmosphere. Of course, the air mass from the ground could be only higher than 1. And so in order to detect the CMB, you have to fit a straight line in this data. These are real measurements. And if you are lucky, you got an intercept that is significantly different from 0. And here you can see the intercept is significantly different from 0 at 2.9 plus or minus 50 milli-K. And so in this case, you have detected something. Okay, the experiment is not very sensitive. This kind of telescope has roughly 1 Kelvin sensitivity. So you get, with some tricks, you have a fraction of a Kelvin, let's say, by integrating a little bit. But it's fun to see that with simple industrial things, you can now detect the CMB. As I said to my students 60 years ago, we would have get the Nobel Prize. Too bad. It's a bit late. So if you're interested, do not hesitate. Okay, let's go back to QUBIC. So in the second part, I will try to show you how we build this instrument, starting from classical interferometry. So first, this slide is just a summary of what is interferometry. So interferometry is to use, in astrophysics, is to use 2 telescopes and to make them interfere. So when you do that, you have here 2 telescopes looking at the given region of the sky. Of course, the light entering one of the telescopes has some phase shift with respect to the other. And when you mix the 2 signals, you get interferences. And what in fact measure an interferometer like that is what we call the visibility. The visibility is given this formula that I gave here. What is it? It's just one of the Fourier mode of the image on the sky. And the Fourier modes of this image of the sky emission is the Fourier mode at a given special frequency, and the special frequency is given by the baseline, so it's given by the separation between the two telescopes. This is the well-known fancy Zernike theorem of astro interferometry. And here it can be also generalized to polarization. You will measure the visibility, so the Fourier mode of the Stokes parameter on the sky. So what is it why is it interesting for astronomy? Because you can do what is called aperture synthesis. So in this case, instead of using just 2 telescopes, you use n telescopes. So you can build n to -1 over 2 baselines, so lots of baseline. And you need multiple baseline in order to cover correctly your Fourier space. So here I use this illustration that I got from HISO to illustrate this aperture synthesis. So this is an example for different telescope planes. What is the image that you will get at the end? So if your telescope plane is too narrow, you will get only the very large periods, so the small frequencies, and so you have some difficulty to recover the image. And as you increase the covering of your telescope, you get more and more frequency information up to the stage where you get and you can recognize what you see on the sky. And if you go too far, of course, you will not be able anymore to measure the small frequencies, special frequencies. You just see here high frequencies, and it becomes tricky to see again the image. And this is called synthesized aperture synthesis, or what you have here is the synthesized image. So from the different Fourier modes, you come back to the image just by doing an inverse Fourier transform. It's easy to say, but it's more complicated to do in reality because you have access only to few modes of the image. But that's something that is feasible. This is well known for several years. If you are interested in details in interferometry, I recommend you these books, which is very useful and lots of information on that. Okay, starting from that, how it is built in reality. So usually it's done by using multiplicative interferometry and with coherent detection techniques. So you have your 2 telescopes here, and after you can use heterodyne architecture, so just to decrease the frequency of the signal, radio signal that you want to measure. So you have a local oscillator, and you mix the signal from each telescope with this local oscillator so that you have a lower frequency at the output of this mixer here, and you can amplify. And after you have a correlator, which is again a kind of a mixer that will give you the visibility at the output, and you can add an instrumental delay here, so it's a phase shift, in order to recover the real part and the imaginary part of your visibility, because visibility is a complex number. All these kind of devices are available in the radio wavelengths. And so why is it interesting to use this kind of techniques for CMB observation? First of all, the thing is that this is a differential measurement. Okay, you measure directly from this integral. What you measure directly is a Fourier mode on the sky, so it's a differential measurement. And so this is something interesting because it removes the common modes. It's also a direct measurement of the Fourier modes on the sky. It's a direct measurement of the power spectrum. You are directly a point in the power spectrum that you want to measure, with, of course, some window function. You can have very simplified optics. You can have just 2 horns looking directly on the sky. So expected reduced systematics, because the optics is much more simpler than classical imagers. And in fact, these are already being used for CMB polarization observation. I remind you that the E modes have been first detected by 2 interferometers. It was CPI and DAISY in the early 2000. These are the paper here given. This is the DAISY experiment from South Pole, and this is the CBI experiment from Chile. And they have been the first instrument to detect the E modes. The limitation of this kind of technology are twofold. The first one, since we want to measure the CMB has no spectral feature, so you need a wideband. And to do wideband with this kind of radio techniques, you have to split the wideband into subbands before doing the correlation. And so the scalability of this kind of techniques is very difficult to make. And also the second limitation is the sensitivity. So coherent detector, since you are sensitive to both amplitude and phase, you have what is called the quantum tax. So you have a lower, you cannot have a noise as low as you want because of this quantum tax. And so the sensitivity is limited with this kind of detection. So the question is, can we try to use this technique with classical direct detectors like bolometers so that we get back the sensitivity that we are losing with radio detectors? This is an idea that has been brought by Peter Timby and Lucio Piccirillo about 20, almost 30 years ago. Again, the motivation is the sensitivity with low temperature detector and the systematic control with interferometry. So how you do that? So this is the sketch. You have your two telescopes, two horns looking directly on the sky, and instead of multiplying the two signals, you are adding them. So it's adding interferometry. You add a phase shifter in between, and you observe what this superposition of the two signals with a direct detector, with a bolometer. And by using the phase shifter here, you can recover again the real part and the imaginary part of your visibility. If you want to be sensitive enough, you have to add lots of horns on the sky. And I can just sketch that here on the bottom. So again, CMB modes, as I mentioned earlier, are dominated at very large scales, around degrees, 2 degrees, something like that. So if you want to observe this feature at 2 degrees and have a maximum of a signal, what you have to do is to have a close packed horn array. And if you have a close packed horn array, as the one as you can see in here, you can deduce directly the UV plane that you are covering. This is the UV plane that you are covering, and these two frequencies, special frequency, can be converted into L space. And roughly the baseline that you need when you are working at 150 gigahertz, 2 millimeter wavelengths, as roughly a few centimeter baselines are enough for doing the science that we do. But we need a lot of this baseline to be sensitive enough. And the color code that you see in here is the number of baseline that is covering this given frequency, 2D frequency. So you see we have lots of baseline covering the low frequency, and it becomes lower and lower as far as you go to largest frequency. That's it. Okay, so you need lots of baseline at that. How you do the interferometry in this case? So you have a lots of horns. With an OMT, you can separate the two polarization. You can phase shift the two polarization independently. You have to add all of that together, and after detect that with your detector. So the mixing here could be done with what is called the Butler combiner. Butler combiner is something that is quite also well known for in radio domain. It just at the end you have just a linear combination of all the entrants. At each output, you have a linear combination of all the signal at the input. So this is exactly what you need. So in order to do that, the difficulty now is to get back the visibility on the sky. So to do that, we use the phase shifters, and you phase shift at different frequency is each horn so that you can recover the visibility at the end. So here there is another trick. You have to find a nice phase shifting scheme. And in fact, there is one. We can use what is called the coherent summation of equivalent baseline. So again, in this horn array here, you have a lots of baseline that has exactly the same vector when you are looking at especially in the low frequency. And if you have this specific phase shifting scheme, you can just add directly all these equivalent baseline and have directly this equivalent, the summation of this equivalent baseline at the output of your instrument, and that already gives you some gain in this architecture. But you can see there are still two limitations for this kind of architecture. It's quite complex to build. We need here. This is what we are here. We have an array of 20 by 20 horns, so 400 horns, meaning you need a Butler combiner with 800 input and 800 outputs that start to be quite complex. So large Butler combiner are difficult to produce, and also the phase shifters is something that probably need quite a large R&D effort to produce this kind of thing. So what is the solution here? So the solution first to the Butler combiner is very easy. In fact, what you can use for the beam combiner is just a classical telescope. Classical telescope is also known as a FISO combiner. If you take, for example, what we have used on QUBIC in here on the right, you see that if you take one bolometer on the focal plane, each bolometer is looking at the superposition of all horns, okay? Because the horns are located in the entrance pupil of your instrument. This has been also implemented on another instrument that has been built by colleagues in the Wisconsin, by Peter Timby groups, especially University of Madison, Wisconsin. This is the MBI instrument that has been built 20 years ago and has been tested also. And we also contributed to the measurements. But okay, actually, if you look at this instrument, if I remove the horns, I have an imager. It's a telescope, so it's a classical imager. So what I do here, in fact, with this kind of architecture is just filtering Fourier modes at the entrance pupil of the instrument. So finally, this instrument is an imager, but it's a kind of a special imager. It is what is called a synthesized imager because you are filtering the Fourier modes at the entrance of the instrument. But again, if you remove the horns, you have a classical imager instruments. And let me see. Okay, yeah, I get it. Sorry. So this synthesized imager, now we know it's a specific kind of imager. What is the point spread function? So point spread function is just the response of your instrument as a plane wave input on your telescope. So point spread function is just the absolute square of the Fourier transform of the aperture field. Okay, the aperture field is given by the horn array. This is the cubic horn array, the real one. And what you will have on each horn entrance here is a Gaussian illumination. And so from that, you can do the Fourier transform and get the point spread function. So if you open just two horns, you will get this image on the focal plane. So it is classically just the classical experiment when you have two holes and you measure the interference of two holes, you get this kind of things. So now if you open more holes, you will add more and more baselines. And in fact, what you see appearing here is what is called the synthesized beam. And if you add all baseline, you get a beam at the center here with replica around the beam. And if you do a cut of this beam, you have this shape here. So it may beam at the middle that is given by the size of your horn array. And you have some peaks also on the side that are located at a length that is given by the distance between two horns. And if you add on top of that also the fact that we are working in large bandwidths, roughly 30% bandwidth, you see that these peaks here will cover some angular distance. And so you see the peak here that produce this kind of shape on the side. I will come back to that because there are some information that could be used we see on this peak. Okay, so we have a classical imager now. What about the problem of the phase shifters? So, okay, since we have an imager, instead of using phase shifter, which require a huge work in R&D, we decided to use a classical way. Classical things to measure polarization is to use a rotating alpha wave plate instead of this phase shifter. By using a rotating alpha wave plate, what you will have at the focal plane of the instrument is just a summation of the total intensity plus the map in the parameter Stokes Q modulate at 4 times the rotation frequency of your alpha wave plate, and the map in the parameter U modulate at 4 times the frequency of your alpha wave plate. So now the question is, what is left of interferometry in this design? Finally, we have a classical imager, we have an alpha wave plate. It looks like a classical imager. Two things. First things is the self-calibration. So self-calibration is something that has been studied a lot in the 80s and the 70s, because with interferometer, you have a classical characteristic, which is fast closure of an interferometer. If you are using 3 interferometers, the phase shift between the 3 baselines is not independent. And you can use that to constrain the signal and to obtain the synthesized image more accurately. And since you have multiple aperture, you have a large number of visibilities, much more than the number of physical parameters that you can get. And so you can infer from that some characteristics. And this is a very specific things that you can do with interferometer. For bolometric interferometry, what we saw directly with this experiment is what we call the fact of using the equivalent baselines. So here on this graph, I show you 2 equivalent baselines. I already spoke about equivalent baseline, but here you can see 2 equivalent baselines. And if in some way we are able to close all the switches but the A and the B in this scheme, we should measure on the focal plane some interference pattern like that. If I open just C and D, I should obtain an interference pattern like that, but in fact, it's the same Fourier mode on the sky, so I should measure exactly the same. If it's not the case, it means that you have some parasitic signal coming from the instrument. So we can model this instrumental systematic error, and by doing, you see, there are lots of equivalent baseline on the array here, and you can invert the problem and deduce the instrumental systematics from these measurements. And again, this is something that we think is very unique to this kind of technology, and that we have published in this paper. Another characteristic, second very interesting characteristic, is the fact that, as you have seen, the synthesized beam depends on frequency. The peak that you see, the secondary peak in our synthesized beam depends on frequency. And we think that this could be used to have an extra information. So we have spectral information. Here, this is just schematized here in this graph. You see, I have two sources, one at 140, one at 160 gigahertz. And we see the 2 sources here on the second peaks. And we think that we can use that to recover spectral information with QUBIC and do multi-frequency map making just from the TOD. There is no hardware modification. It's just data processing. So instead of having 2 bands at 150 at 220 gigahertz with a given sensitivity, you will get few bands just in data processing. Of course, the sensitivity will be lower. That's normal. Okay, but you recover some spectral information from these. Again, same hardware, no specific modification. It's just CPU times. Oh, and that's it. Okay, so we need more CPU times as usual. Okay, I will speak about, maybe give you more details in the last part of my presentation. Okay, last part is the sensitivity of bolometric interferometer to beam modes on the sky. The specificity of bolometric interferometry is that the sensitivity depends not on the number of detectors you put on the focal plane, but on the number of horns that you put at the entrance of your instrument. As soon as you assume that you have enough detector on the focal plane to sample correctly the synthesized image. If you have that, the sensitivity depends on the number of horns. And we have made, so this graph is a bit complex to read, but this is the multiple. And this is the ratio between the sensitivity of an imager divided by the sensitivity of a bolometric interferometer. And when you are below 1, imager is more sensitivity, or above 1, bolometric interferometer is more sensitive. What we see, of course, is depends on, you have different assumption of especially on the scanning strategy of the instrument. But what we see roughly that bolometric interferometer has a lower sensitivity, but close to classical imager. My understanding of that is very simple, is that, in fact, each horn has a given effective area that is not the physical area. And so you have a little bit of a loss in there because you are not using all the area of your entrance pupil as you would get with a classical imager. But putting all together, okay, a loss maybe of maybe 20 or 30% in sensitivity. If we have some gain, in systematics effect, why not? And so we decided to build a prototype instrument, and this is the QUBIC instrument. So QUBIC is a large collaboration, and between France, UK, Italy, Argentina, and we have also colleagues from MBI, especially Peter Timby, that join us. And the instrument is located at San Antonio de los Cobres in Argentina, not far from the Chile Observatory, in a altitude site. So the QUBIC concept. So you start from the sky, and first you modulate the polarization from the sky with a rotating half-wave plate, and after we use the polarizing grid. So here we lose half of the photons. We decided to do this to simplify the architecture of the instrument. You enter the horn array, and the horn array are recombined with a telescope made of 2 mirrors. And after that, the light is focused on 2 focal planes, 150 Hz and 220 Hz, by use of dichroic in the middle. This has been designed in a cryostat. You can see here a cut-off view of this cryostat. And as I've shown you, when we open one horn on the focal plane, we should have this kind of illumination. 2 horns, you have the classical interference pattern of 2 horns. And when you open everything, you have the synthesized beam that we have you have measured in calibration, especially. So these are photo of the cryostat, quite big cryostat. So right now the instrument form is what we call the technological demonstrator. So it has exactly the same cryostat and the same cryogenic as the final instrument, but we have a smaller horn array. We have only 8x8 horn array, and just a quarter of the focal plane is filled with detectors. These are TESs, transition-head sensors, that are cooled at 320 milli-K. I will come back to that in a few slides. And we observe at 150 gigahertz. And so this instrument has been integrated and tested at APC, sent to Argentina, and is now on the observation site. Just some slides on the detection chain. So the focal plane is divided in 4 quarters. Each quarter consists of 256 TESs, transition-head sensors, cooled at 320 milli-K. We'll reach 320 milli-K. And after this quarter are also divided in 2. So we have 128 detectors that are read out in a time domain multiplexing by 128 squids, pulled to 1K. And we have after that one ASIC, silicon germanium ASIC, cooled at 40K to control the TDM multiplexing scheme, and an FPGA board at 300K to digitize the data. Okay, that's it. These are the detectors that we are using. So this detector has been produced and designed in Orsay, so nearby Paris. It's a TS array based on niobium silicon. So you see here the thermal sensor is niobium silicon, so a superconducting material, and the wires used are aluminum. You see the wire grid here that absorb photons, and here another picture of these detectors. So we have demonstrated on prototypes an EP of 510 to the -17 watt per square root of Earth with this kind of detectors. It is a picture of a wafer that is integrated on an holder, and this holder has been implemented on the focal plane of QUBIC. You can see here the primary mirror, and the secondary mirror should be somewhere here on the top. And the readout scheme, so it's based on time domain multiplexing. So the scheme is based on 4 columns. So we put 4 columns of squids. So we have the squids in series, so 32 squids in series here. And the ASIC will bias each squid one after the other. When the squids are not biased, they are superconducting. And we amplify the signal coming from this column of squid by a low noise amplifier, also located in the silicon germanium ASIC. And by switching from one line to the other and from one column to the other, we are reading each detector one after the other in this scheme, as is classically done with time domain multiplexing. So the squids are squids from Star Cryo-Electronics, slightly modified. You can see here the squid board. The silicon germanium ASIC has been designed at APC. The squids are, I don't know if it's clearly here, it's there. The squids are biased through capacitor here so that you are not producing any Johnson noise. And also the low noise amplifier in the ASIC has a noise level of 0.3 nanovolt per square meter of hertz. And you can see the noise measure on this amplifier at low temperature. And everything is controlled by an external clock. So roughly on this ASIC, you enter an external clock and in control the multiplexing. You can tune, of course, some parameters, the current in the squids, the number of detectors you want to tune, you want to measure, etc. But that's all integrated in this ASIC. And the FPGA board does the acquisition at room temperature with ADC and DAX. And we have implemented the digital flux loop operation of the squid as well as finite modulation. Finite modulation because, as you can see in this graph here, our low noise amplifier has some 1/f noise at low temperature. The white noise of the ASIC LNA is better, but the 1/f noise is also higher. So we needed to implement some flux modulation in order to beat this noise, this 1/f noise of the ASIC especially. So this is a measurement that has been done in SALTA, this one. So SALTA is the city nearby the observation site. It's lower in altitude, and we shipped the instrument there first to test and to check that everything was working correctly before bringing the instrument to the site. So from SALTA to the site, it's about 3 hours drive. And this is a measurement of IV curves. You can see IV curves on all of most of the detector. We have a yield of about 77% measured in SALTA, with a readout noise that is currently limited by aliasing from the multiplexing. So this is something that was known in the beginning of the project, but we decided to live with that because of limitation in human resource. So we noise that is limited by noise level of 100 picoampere per square root of hertz. Because of this aliasing, we plan to implement Nyquist inductor in order to implement that in the near future. We also had some issues with sensitivity to microphonics and the instrument. So due to pulse tube, I will switch. I see I'm a bit late. I will skip this part. If you are interested, I can come back to that later. But because of that, we are limited roughly to few 10 to the -16 watt per square root of hertz in the sensitivity on the instrument, which is not perfect. But we think it's enough for the technological demonstrator to demonstrate that the instrument is working correctly. We characterized the telescope and the instrument at APC before shipping it. We measure the bandwidth. We also measure with the rotating alpha wave plate the cross polarization, and we measure very, very good cross polarization level for the instrument, better than 0.6%. For the instrument. We measured also the synthesized beam. This is the synthesized beam that we measure at different frequency. You see the evolution of the synthesized beam as a function on frequency, sorry. And this is just the synthesized beam in false image. And as I showed you previously, it is the basic of the spectroimaging. We see the secondary peaks position depends on the frequency, and this can be used for the spectral imaging part. Concerning the self-calibration technique, I told you, okay, so the idea is to have only 2 horns open and to observe the interference on the focal plane. So to do that, we build RF switches. So in between the back-to-back horns, we place this part that you could see here, which is a system based on electromagnet and blades that will open or cut the waveguide. You see here the waveguide, as you see. It is the circular waveguide from horns, and you can open or cut, or close, sorry, this waveguide with this electromagnet, and this is working at low temperature as well. So because of heat dissipation of these electromagnets, what we are able only to close, if I remember correctly, four horns all together. But there is a trick here. You can do the math, and you can demonstrate that by measuring four images, one horn open, the other open, the two open, etc. There are some mathematics there, but you can recover the information that you need. And this is what we did during an example of the basic of self-calibration. So this is what we measure on the focal plane. So you see the interference pattern. That is what the simulation would give, and this is the basic of the self-calibration. So we tested that as well. And so the instrument has been installed on the observation site. So you see here the instrument on this Alto Chorrillo site. So it is at 5,000 meters above sea level. In Argentina, we have had a first commissioning of the instrument. So this is the pull down curve. So this is the 4K stage in red. So in blue, this is the 1K stage, and in green, this is the 300 milli-K stage. And we had roughly 50% cryogenic yield, and I have some idea to improve that as well. It will be done in the near future. And we had also lots of measurements and also some improvement on the experiment, but because of different reasons, especially political reasons in Argentina, we had to switch off the cooling of the instrument, unfortunately, in the mid-2023, and the instrument is still off now. We wanted to start again the instrument recently, and we had some issue of vacuum leaks on one of the flange, and so we are replacing this vacuum flange right now. But the site is still being improved. So recently, the calibration tower has been implemented on the site. You can see here the calibration tower. This calibration tower, on this calibration tower, we'll have the calibration source on the top, so that we will do the self-calibration technique using this source on the top. Just to finish, if I have 2 minutes, I want to give you some idea of the spectral imaging. So again, the spectral imaging use the fact that this secondary peak depends on frequency, and we can make a simple calculation on the number of independent bands that you can get from this. And with the technological demonstrator, we expect to have 3 bands, but for the final instrument, we should be able to have 6 bands with this architecture. But to do that, what you have to do is, from time order data, you have to have a map-making algorithm which will take into account the fact that your beam depends on frequency. So first, what we did at the beginning, we defined the map-making algorithm, not taking into account the fluctuation of the secondary beam with respect to frequency, and this was working correctly. And so we generalized that to multi-frequency map making, and this has been published in this paper. And in fact, this kind of measurement is very similar to what is done with what is called the Grism spectroscopy. So maybe, I don't know if you know what it is, but Euclid, the satellite Euclid that has been launched in last July, if I remember correctly. So he's using in front of the detector a kind of dispersive element, so that instead of having this kind of image, what you will have is for each object on the field of view, a spectra of this object that will be present here as a dependence on the position on the image. And what we have for QUBIC, it's exactly the same. We have the secondary peak that depends on frequency, and so it will add some slight lines like that in the system. So we build these map-making algorithms. So from TOD, we have done some simulation. You are able to divide your 150 gigahertz in this example in 5 bands and recover the spectral information from that. We went also a little bit further to that. We build because the spectral information is already implemented, is already there in the time order data. You can build directly components from the TOD. Instead of building maps, you can build components from this TOD, and we also demonstrated that recently in this paper. So in terms of real demonstration of that. Right now, we have this first measurement we did at APC. So just by using this algorithm on the calibration source, we had this map of the calibration source at 150 gigahertz, and we see the source at 150 gigahertz and not present in the other maps. We also had a first try in Salta. So we observed the moon in Salta. So unfortunately, Salta is not very high. Maybe it's 700 meters above sea level. So the atmosphere is not very transparent, but we were able to see the moon. You can see here the moon measured by QUBIC. These are the trees that were there at the moment. And we see here the secondary peaks. And we made the first try to recover spectral information of the moon by using these peaks. But of course, this has to be improved, and we hope to do that from the site as soon as possible, because we think this is a very interesting feature. Okay, just to give you also again, why it's interesting, okay, because when you are using a classical imager, for instance, at 150 to 20 gigahertz in this example, you have only 2 points in this case. Well, if you add spectral information, you can have much more information and check if you have some contamination for foregrounds, okay? And this is especially very important if you have a complex foregrounds model. For instance, we have demonstrated also in simulation, by using this spectral imaging technique, you can break some degeneracy when you have complex dust model, as for example, dust decorrelation that is seen in here. I go fast because I'm late, but if you have more information, I can give you some answer. Okay, to conclude, so QUBIC is the first bolometric interferometer for CMB polarization observation. I tried to explain you how we build this instrument from the scientific objectives to the architecture of this instrument. The sensitivity, we expect a sensitivity of roughly R of 0.015 with 3 years of integration time. And we have several specificities with classical imager. So we have the self-calibration technique. We have low cross polarization because of the simplified optics. And also the spectral imaging techniques, which we think is really a new path for foreground mitigation. And if you are interested in the instrument, we have published recently this bunch of 8 papers covering the forecast, the lab calibration, the hardware design, and we also published recent paper on these spectral imaging techniques. Okay, thank you for your attention.
Thank you so much. So we're going to take questions now. We will start with a question in the room, and then we'll move on to questions from Zoom. So anyone in the room want to start us off? John?
Well, thank you. Great talk. So maybe this is really simple, but I'm curious about the close packing of your horns. You talked about how the fact that the sum of all the aperture areas doesn't equal the image plane is limiting your sensitivity. So I'm curious, why aren't the horns hex packed? Wouldn't that...
Well, the horns what?
Why aren't they hexagonally packed? Wouldn't that give you an extra 20% or something?
Okay, so we try. So what we did is we had a look at the UV coverage of the hexagonal pack. From what I remember, it's the number of equivalent baseline is not as good as a square packed array. Okay, and what is important in the sensitivity, you can have a look to the sensitivity paper of bolometric interferometry, but the sensitivity in the L domain is given also by the number of equivalent baseline at a given L. Okay, and so we decided to go to a square wave because of that, because of this number of equivalent baseline was a little bit higher in the L domain where we were interested in.
So if I may follow up, is that mathematically optimal in some sense, or is the square pack kind of like an engineering decision?
You just do an histogram of the baseline on your horn array and look at that's
okay.
The optimization done.
Okay, no one on Zoom yet. Okay.
Sorry, this is maybe a naive question, but I kind of got a little confused because I think of interferometry, I think of narrow band, particularly, I guess that's with longer baselines. If shorter baselines, maybe it's less, but where does your energy or frequency resolution come from? Is it just from being able to add things up coherently, or does the detector have, do you have energy measurement to measure frequency of the individual photons?
So you mean the angular resolution or the spectral resolution?
The spectral resolution.
Ah, the spectral resolution. So the spectral resolution is maybe I went a bit fast on that, but so the spectral resolution is given by the angular region that you are covering here, and this angular region is given by the wavelength, the bandwidth of your instrument divided by the distance between two horns, while one beam is given by the size of the whole array. So to get the number of independent bands, you just have to divide these two. In other words, you have to compute the number of equivalent peaks that you can put here in this area. Yeah.
All right, one down there. Sorry.
Yeah, another basic question about the spectral imaging. What is the sort of calibration done for the power in each spectral band? How do you know that you're accurately measuring the power in each sideband?
So calibration will be done so the calibration roughly, as you can see in here, is given by the shape of the primary beam. And the shape of the primary beam has to be known very precisely, because if you want to do the map making algorithm accurately, you need to know the beam very, very well. And so the beam will be known very well by using the calibration source that will be installed on the mast. And so you will see the shape of the beam, and so you can use that. And after, of course, we will calibrate on the CMB.
I have a quick one. You alluded earlier to an issue with the pulse tubes affecting the instrument. Can you talk about that?
Yeah, I went fast on that. Sorry. So this is So an example of what we measure. So this was measured in Paris. So you see the signal on one bolometer, and when we turned off the pulse tube, you see the noise that decreased a lot. Okay, if you are some experimentalists in the room, they are probably they know pretty well know this problem. And so so what has been, we attributed that to some excitation of mechanical resonances, because what is very interesting in this measurement is you see that the signal increased a little bit when we stop the pulse tube. On the top here, you see the signal is increasing, meaning that the detector temperature decreased a little bit. So the pulse tube is dissipating power directly. So there is a way. There is some So let's say that vibration are dissipating power directly on the detector, and that's why you have this cooling of the detector at the beginning, and after the curve goes down because the temperature is rising. It's reverse, and so we attributed that to this heat dissipation directly on the detector. So what we plan to do, the problem is that the pulse tube was not enough mechanically decoupled from the cryostat, especially on the first stage. On the second stage, we use copper braids. We were very careful on that, but on the first stage, it was already implemented, and so we were not able to modify that. So we think it's come from that, and we plan to implement and to improve that for the final instrument.
Okay, I think unfortunately we're out of time for questions. So if anyone has anything to follow up with Michel, he's here in the 50 complex for the next 6 months or so go bother him. But thank you very much, and let's thank our speaker again.
Thank you.